Next, we have Butler Lampson, who is a technical fellow at Microsoft and an adjunct professor at MIT. He is a Turing Award winner from 1992, and he was SOSP chair in 1971. And he has been part of this OS community from the very, very beginning and has played a key role in many of the core pieces of computer systems that we take for granted today. Time-sharing systems, local area networks, WYSIWYG editors, so many things. He was part of the highly influential Xerox PARC lab. He's responsible for the classic hints for computer system design that we all think of as the Bible. And today he's going to be talking about a condensed account of the checkered history of computer security from the 1950s to today, how we got in this mess, and how we might get out of it.
I just wanted to mention that I was actually co-chair of the 1971 SOSP. I was extremely lucky to have another co-chair who actually did all the work. So that was pretty much ideal. So here's the view of computer security over the last 50 years from a geosynchronous orbit. In the beginning, it was easy. You got your security by physical isolation. You brought your data to the machine on a paper tape or whatever. You had physical control of the machine, and there was some printout or something that you took away, and that was it. And we still do this today. It's about the best form of security you can get is to either actually do it that way with your own air-gapped machine, or do it with VMs and cryptography and maybe enclaves. Then in the early 60s, time-sharing came along, and it brought us for the first time the basic dilemma of security, which is the conflict between isolation and sharing. And that's hard, because in this world, every user wants their private machine that nobody can interfere with, but they also want to share things. And since then, I think it's fair to say things have gotten worse pretty steadily. Security has gone downhill ever since CTSS. We have less isolation today, more sharing, no central management, more valuable stuff. And we've made this terrible mistake, which I think was caused by the fact that for 20 or 30 years, the NSA funded almost all the work on computer security. And that is the search for perfection. Well, perfection, unfortunately, is not to be had. So my favorite saying about security is the one at the top of this screen. This is Air Force General Jude Law, who said in the mid-50s, nothing to do with computers. He said, if you want security, you must be prepared for inconvenience. Well, we're not prepared for inconvenience, and that's the fundamental reason why we don't have security. So over all this time, here's what we've learned how to do. We know how to secure something simple really well, and we can also secure something complicated if you isolate it. We're also very good at staging security theater. We work hand in hand with the TSA. And both communities give rise to lots of headlines. What we don't know how to do is to make something complicated secure, make something big secure if it's not isolated, keep something secure when it changes. We're no good at getting users to make sensible judgments about security. Often people recommend better user education. The users are completely rational about this. They see no value in security education, and they're not going to do it. And also, we don't understand privacy, but fortunately, I don't have to talk about that. OK, so that was the view from geosynchronous orbit. Now, here's the view from low orbit. You can think of this as a summary of everything that I have to say, everything that's happened in security in the last 50 years. There are the basic goals of security, which are secrecy, integrity, and availability. And for some reason, secrecy got replaced by confidentiality. This must have been some military hang-up, that secrecy was special and you wouldn't be allowed to use it. But a two-syllable word, three-syllable word's got to be much better than a seven-syllable word. So I've refused to accept that. Although I do have to admit that with confidentiality, integrity, and availability, you have CIA as the acronym, which is charming. There's the gold standard for access control, which is authentication, authorization, and auditing. We'll have a lot more to say about that. There's the basic idea of principles, and there's the idea that you have to group things together if you want security to be manageable. And then there are these fundamental oppositions. And I've arranged this table so that the party that has been most successful in actual deployment is on the left. It doesn't mean that convenience is better than security. I'm not taking a position on that. But definitely convenience wins over security. Sharing wins over isolation. That's why we have so many security problems, is that we share things that it would be better not to share. Bug fixes win over correctness for reasons that we'll talk about briefly. Policy and mechanism wins over assurance. It's much easier to invent features than it is to make sure that the features you already have are actually working. And access control wins over information flow. So I made this slide because I was thinking for a while that I would give a historical account of what's been going on. But I abandoned that idea. And so this is all the sort of clear chronological history that you're going to get. We're now in an airplane flying over the landscape. We're not in orbit anymore. But what you can take away from this slide is the boldface in the middle column. We started out doing time sharing in the 60s and 70s. Then in the 80s, we had workstations and client-server computing. In the 90s, the main issues were PCs and the web. And the web, of course, has continued to be a central issue in security. In the 2000s, the advent of JavaScript introduced all kinds of new problems. And then in the current decade, we have big data, which introduces even more problems, mainly of the form that the big data is a much more attractive target for the bad guys. So I'm not going to do a timeline. I'm going to do important concepts. And the foundation of security, unquestionably, is isolation. If you don't have isolation, there's no hope for security. You have this big system with everything interacting with everything else and no isolation. You're just going to be out of luck. So the basic idea of isolation is you have some sort of a host that isolates one execution environment from another. And it's unavoidable that you have to trust the host to do that properly. Whether the trust is justified or not is another matter. And you can do isolation at many different levels. Working from the bottom, you can use physics as the host and use air gaps, physical separation of the machines. And you can do it on the network. You can do it with virtual machines using a hypervisor, and so on up. And the basic ideas of security are pretty much independent of what isolation mechanism you use. Some of these mechanisms are easier to get right than others, mainly having to do with the complexity of the interface between the host and the execution environments. So doing it at the OS level for an OS like Linux or Windows, for example, is extremely difficult because the interface is quite wide. Doing it at the VM level is much easier because the interface to the underlying virtualized hardware is much smaller. Okay, so that's the foundation. Now we'd like to, granted that we know how to do isolation, now we'd like to do sharing, and we'd like to do it safely. So the basic ideas here were worked out in the late 60s and early 70s, and you can find them all in one way or another in the classic Anderson report that was produced for the guidance of military funding of computer security, R&D. And the basic notion is one that probably is familiar to most of you. Look at the top line in the chart. You have some sort of originator of requests, a subject or a principal, which generates requests. The requests go in across some isolation boundary, and they're looked at by a guard. The guard is paying attention to the policy that is supposed to be enforced. And if the guard passes the request, then it goes to the object or resource, which can carry it out. So that's the basic story. You can break you can break this down in various ways, but here's the sort of classic way of doing it, which I call the gold standard because all these things start with AU. The left-hand side of the picture is authentication. What you do is you authenticate principals. You try to answer the question, who made this request? And the answer to that has to come in some form that the guard can understand. So people can make requests, but also channels, servers, programs can make requests as well. The right-hand side of the picture is about authorization. Who is trusted to do something with the resource? And the guard's job is to put together their information about who made the resource with information about who's trusted, who made the request with information about who's trusted to access the resource in order to make a decision. And to make this authorization feasible, you need to group the principles and the resources in order to simplify the management. And finally, an essential part of the whole thing is auditing. You need to keep track of what resources were granted or rejected so that when later you figure out that something went wrong, you can go back and find out what it was. And auditing is a topic that's not very sexy, and the community as a whole is way underinvested in auditing, in my opinion. What about the policy? How do you decide what sharing is allowed? Well, this is the classic story that I put together in 1970 for the co-signed Committee on Operating Systems. I came to the committee and I said, the guard should be evaluating a function. You feed in what Peter Denning later called the subject and the object, and the policy function tells you what permissions, what operations are going to be allowed. The committee said, functions? No, that's much too mathematical. Our students will never be able to understand that. We may not even be able to understand it. So I was a little startled by that, but I went away and I came back to the next meeting and I said, okay, forget functions, that's too complex. Let's have an access matrix. And that caught on. And here it is. You have the subjects down the left-hand side and the objects across the top, and the boxes tell you the values of the function. There's a number of different ways to interpret this. The classic ones are with capabilities or with access control lists. So if you keep the permissions with the object, then you have access control lists. If you keep the permissions with the subject, you have capabilities. And both of these have been very successful, but in different domains. Capabilities work for short-term policy, and all operating systems have them, although the popular ones don't call them capabilities. Unix calls them file descriptors, Windows calls them handles, programming languages call them objects. And this works really well for short-term. It's no good for long-term for a very fundamental reason, which is the question you normally want to ask about your policy is, who can do things to this resource? And access control lists answer that question, and capabilities don't. So they don't work. Capabilities don't work for long-term security. There's another approach to security besides the classic access control approach. And this one is called information flow. And the idea is that instead of controlling access to resources, you control where information is allowed to flow. So if you look at this picture, you'll see that it's very similar to the access control picture that's in the lower right-hand corner, reproduced in the lower right-hand corner, except the top row has been kind of flipped. So in information flow, you add labels to the data, and the guard's job is to decide whether it's okay to send data with a particular label out to a particular subject or not. This scheme was invented to model the military classification scheme. So the basic idea is you label every datum, top secret / nuclear is more highly classified than top secret, which is more highly classified than secret, and so forth. The labels form a lattice, and they propagate in the sense that if you feed data into some computation, then the label on the output has to be the max, at least the max of the labels on all the inputs. And people worked out schemes for enforcing this with access control by labeling the subjects and the containers and making a rule that data can only flow upwards from a container to subject to other container. And you can do this in a variety of different ways. Various attempts were made to implement this, and they were all pretty much unsuccessful, and this subject kind of died out, and then it was revived about 15 years ago by Andrew Myers and Barbara Liskoff, who introduced an idea that I don't think the military would ever have thought of, which is that you could have decentralized flow control. Anyone could invent labels, and if you own a label, then you control it and you can declassify it. And this has given rise to a lot of interesting research. So far, I think it's fair to say none of this stuff has been practical. And that's even when you don't consider the problems of so-called covert channels, which are channels that you can't find out about by reading the manual. They're ways in which information can be transferred by observing timing, radiation, power, or so forth. And the basic difficulty that gives rise to covert channels is that, for the most part, abstractions are not designed to keep secrets. this covert channel thing got started in the intelligence community, which introduced a standard called Tempest for protecting digital systems from being snooped on by the electromagnetic radiation that they generate. And there's a story that the intelligence community has competing intelligence agencies, and they're not very friendly with each other. And one of them figured out how to do this, and they built a whole bunch of equipment for doing it, put it in a truck, drove this truck into the parking lot of a rival agency, and sat there and waited until they were able to zero in on the radiation coming from an impact printer, which was a relatively easy thing to do because an impact printer has big magnets that slam the paper against the type slugs. So they started reproducing in their van the printout from the printer inside the supposedly secure machine room of the rival agency. And when they got something really, really sensitive, they tore it off and they went in and slapped it down on the desk of the director of the rival agency and said, "You guys have a really serious problem." And that gave rise to a lot of uproar. Policy. We've talked about what form the policy can take. The other important question about it is who gets to control it? How can you decide this? Well, the questions you have to ask, the natural thing to say is, well, the user should control the policy, because after all, it's the user's data for some value of ownership. That's called discretionary access control. The object's owner gets to decide the policy. But it's possible that the user or the program that the user is running is malicious. The user might not be competent to decide policy. Policy can be quite tricky. And the user might not be interested in policy. Security gets in the way. So for the most part, people don't pay attention to it. So this has given rise to the notion that there should be mandatory access control, where an administrator controls the policy. And many people have equated mandatory access control with the information flow control that I talked about earlier. But actually, it's a much broader notion. Typically, the information flow control is mandatory. Certainly, it is in the military domain. But there are many other ways to do mandatory access control. And in fact, one way to do it is so-called role-based access control, where the notion is you put the users into groups called roles. And of course, the idea of putting users into groups is an old idea that goes back to Multics. The new thing about role-based access control, it took me several years to figure this out. The important thing about it is that it's the app designer that controls the ACLs. The only thing the user is allowed to do is the administrator is allowed to do is populate the roles. And if the app designer controls the ACLs, it's much more likely that they'll be correct because they'll be designed and debugged as part of the process of designing the app. Okay, so that was the basic story of security. Now, when distributed systems came along, a few things had to be added. Here's the simple thing that had to be added, the notion that in distributed systems, the different parts of the system have to be able to communicate. And so you need secure channels for the communication. Well, it's possible for the host to implement the secure channel if the two parties involved are both hosted by the same entity. But in general, in a distributed system, that's not the case. So you need some sort of secure wire or a simulation of it. Usually you do this with cryptography. And cryptography has a fundamental advantage, which is that it works end to end. You don't need to know anything about the security of the path by which the encrypted bits travel from one place to another in order to believe that the channel is actually secure. So the basic crypto functionality is you can maintain integrity by signing with a key and verifying with another key. You can maintain secrecy by sealing with a key and unsealing with the other key. And the basic property you want the crypto system to have is that you can only do these operations if you know the key. And as I said, the charm of this is that it gives you an end-to-end secure channel. In the mid-'70s, public key crypto was invented. The nice thing about public key crypto is that the two keys are different, so I can sign and anyone can verify. About 5 or 6 years ago, homomorphic crypto was first demonstrated to be practical, I won't say, but feasible. The idea of homomorphic crypto is that you can actually do computations on the encrypted data, so you don't have to trust the computing engine. Previously, the only thing crypto could do was to protect the communication channel. Now it can actually protect the computation as well. Unfortunately, homomorphic encryption is too slow to be practical. But there's been quite a lot of interesting work recently based on the idea that you can actually simulate homomorphic encryption with some very carefully isolated region of the computation that takes in the encrypted data, decrypts it, does the computation, re-encrypts it, and then spits it back out again. And there's also been interesting work on verifiable computation, where I can offload my computation to somebody that maybe I don't trust, but I can check that he's done it correctly. The more interesting and subtle aspects of distributed systems have to do with understanding about trust. And the reason this is important in distributed the reason people first started to pay serious attention to this question in the context of distributed systems is that by their nature, distributed systems are decentralized. You don't necessarily have the same parties responsible for the different parts of the distributed system. So that means that they have to be able to trust each other, and you have to be able to reason about that. So how does this work? Well, there's three basic elements of it. There are principles, which initially were people, but subsequently we realized that machines, programs, services, protocols, any component of the system can be thought of as a principle. The notion of accountability, which is that a principle makes some statement, then you have to decide whether you believe this statement based on whether or not you trust the principle. So canonical example, Alice says, read from file foo. Now, should I actually do that? That's the question of trust. And the fundamental thing that makes reasoning about trust work is the notion that one principle can speak for another. So Alice may say that Bob at Microsoft speaks for Alice. That means if Bob at Microsoft says to do something, you can proceed as though Alice had said it too. Microsoft says that this particular key speaks for Bob. The key says read from file foo, i.e. you get in a request that's been encrypted, that's been signed by that key, and now you can conclude that Alice says read from file foo. A wrinkle that was thought of a little bit later was the notion that you can encode an access control list entry as one of these statements. So file foo says that Alice speaks for file foo. And now, from all of these previous things, you can conclude that foo says read from file foo, which is an appealing sort of end-to-end reasoning. You don't have to make a distinction between the authentication and the access control. They all fit together into the same reasoning structure. And these ideas were worked out by myself and several of my colleagues at DEC, and they've been reinvented a number of times since then. So that was features. Now, what about the question of does it actually work? That's assurance. The basic strategy for assurance is to keep things simple, because if things are complicated, it's much less likely that you're going to be able to convince yourself that they work. Ideally, you get assurance by verifying, by proving that a system satisfies its spec. This was first tried in the Gypsy system by the folks in Texas with moderate success, but enormous labor. And today, we've come a long way in verification. You can actually do successful verification of systems of several tens of thousands of lines of code. If the verification works, the only thing you have to worry about is that the spec might be wrong. The only defense against that is to keep the spec simple. Usually, verification is too hard, so you do certification instead. This has been tried many times. Unfortunately, what usually happens is that process dominates substance, and the certification doesn't really give you the assurance that you want. We don't, typically the systems that we actually use, you don't do either verification or certification. Instead, you do what's called defense in depth. That's the polite name for putting Bandaids on the bugs in your system. And there's a very wide variety of defense in depth techniques that are deployed probably in many of the systems that you guys are running right now. Fundamentally, they're not bad things, but you have to recognize that fundamentally they don't work. And what they're doing is putting you in position of the hunter that can run faster, so the bear will catch the other guy. What these Band-Aids do is make it more difficult for the bad guy to break into your system than to break into someone else's system. And so they change the bad guy's motivations, but they don't actually work. What about policy? I take in one of these secure systems and I deploy it on my hardware, and now I have to express my policy. Or put another way, I have to configure the system somehow. Even if the code in the system is correct, the configuration might still be wrong. And this is a really serious problem because you write the code once, but every system has its own configuration. And furthermore, the configuration is usually done by amateurs. So the only conclusion I've been able to reach from this is you'd like to have very fine-grained policy that says exactly which subjects can do what to which objects, but you can't manage that. You can only manage very coarse-grained policy. So you have to lower your aspiration and essentially have some sort of budget for the complexity of your policy if you want it to succeed. Okay, so what's worked and what hasn't worked? And the definition of worked here has gotten wide adoption. I'm sure we're now back in low Earth orbit. We're away from, we're not in the airplane anymore. Things that have worked: virtual machines, SSL, passwords, safe languages, firewalls, and process has worked pretty well. Microsoft, for example, in the so-called security development lifecycle, has sunk probably a couple $2 billion over the last 10 or 15 years into process, and it's been pretty successful. The goal of it was to keep us off the front page of the Times, and it succeeded. Nowadays, the OPM and Target are on the front page of the Times, not us. So it's been great. Things that have failed have been very popular, things that have given rise to lots of papers in these conferences. Secure systems, we don't have those capabilities. I worked on capability systems. I was one of the designers of the first capability system that actually had users in Cal TSS around 1970. Metrics for security, everyone says we need those, but we don't actually have them. User education doesn't work. Intrusion detection doesn't really work very well. It seems like a cool idea. So just to wrap up, now we're back in geosynchronous orbit. Why don't we have real security? Well, the fundamental reason is people don't buy it. The danger is not that big, in spite of what you read in the paper, so it's okay to buy features instead. Security is expensive, configuring it is hard, and the secure systems have less functionality and worse performance. And security is a pain, because the basic job of security is to stop you from doing things. People don't want to be stopped from doing things. And the goals are not realistic. They ignore both technical feasibility and the realities of user behavior. A secondary reason we don't have real security, which is the one that we typically focus on in these conferences, is that systems are complicated, so they have bugs. But the fundamental reason is that people don't buy it. So what's going to happen next? Well, this is my recipe for what happens next. Lower aspirations. In the physical world, in the real world, good security is a bank vault. And a bank vault is a pain in the butt, and you don't put things in there unless they're really important to you. I can't offhand name any computer system that has anything corresponding to a bank vault. So I have no way of saying these things are really important to me, these other things are not important. We only know how to make simple things secure. So access control doesn't work. We already talked about that. Another way to think about lower aspirations is the slogan retroactive security, which says you shouldn't try to stop all bad things from happening. You should just make sure that when something bad does happen, you can do something about it. And I just offer the observation that real-world security is retroactive. Burglars are stopped by the fear of going to jail, not by locks. And although most people think that the financial system's security depends on vaults and encryption and all that other stuff, actually what it depends on is the fact that almost any financial transaction can be undone. The ones that can't be undone have to be handled much more carefully. So that's all I had to say, and we might have time for 1 or 2 questions, since I've only taken 28 of my 25 minutes.
Worth the extra minutes, and I think I'm going to be reckless and take a question.
Yeah, it's conceivable to me that information flow might work. It may be the problem we've had with it has been that we've been too hard-nosed about it. But certainly its record so far has been discouraging. So I think that's up for grabs.
Okay, the question was, any hope for information flow? Okay, great. Thank you so much. That was amazing. Here's your principal's t-shirt.
Thank you kindly.